Hello, welcome back. In this segment, I wanted to answer this question. How many elements are there in the group Z star n, the multiplicative group that we talked about earlier, which is made of numbers from 1 through n minus 1, such that GCD of any element A in the group with n is 1. Okay, so for example, what is Gn star of say, for example, n being 15? What are the elements of this group? We can say it is group elements 1. The group elements are 1, 2, 3 can't be because 3 shares factors with 15. 4, 5, 6 is not possible because they share factors with 15. 7, 8, 9, and 10 are not possible. 11, 13, and 14. So we have 3, 6, 8 elements. Okay, the number of elements in this group is 8. This is basically the order of the group. Okay, remember Z star n is made of numbers 1 through n minus 1, but not all numbers. Only those numbers that satisfy this property that a GCD of a comma n is 1. Okay, then such an element A belongs to Z star n. Okay, then that's basically what the definition of Z star n is. Okay, all right, let's think about this problem. How do we compute this? It would be nice to have a formula, right? You just send in an n, it tells you Z star n. By the way, this function is studied by Euler. It's also called Euler's totient function. There are multiple notations. One of the notations is like this. Given n as an input, it tells you the output. In this case, when n is 15, the output is 8. Okay, so if you are able to find an efficient formula that can solve this problem, you have essentially broken some crypto systems like RSA. Okay, it's not clear whether there are any polynomial time algorithms for large n can tell you right away how many elements are there in the group. Okay, and nevertheless, I would like to talk about if you know the prime factors of n. If n is a composite number, we can easily compute the pi of n if you know the prime factors. But if you don't know the prime factors, excuse me, then we don't know how to solve this problem, which is one of the assumptions in RSA is that given n, it's not easy to compute pi of n in a reasonable amount of time. Okay, that's something to keep in mind why this problem is interesting in cryptography. Okay, but if n is prime number, it's easy because if n is prime, all numbers below n will have this property, right? Will satisfy this property. Okay, for example, if you take n to be, say, 7 is a prime number, then Z star n will have 1, 2, 3, 4, 5, and 6. Okay, so the answer is whenever your number n is a prime, we usually write it p. Okay, anyway, pi of n is nothing but n minus 1. Okay, so I'm going to use notation p to show to you if it is a prime number, the order of the group is easy, it's p minus 1. Okay, but if it's a composite number, we don't know how to compute it. And in this segment, I want to talk about computing pi of n if you know the prime factors of n. Okay, all right, let's get started now. So suppose you know your number n is made of 2 prime numbers p and q. Okay, the question now is, how many elements are there in your group Z star n? Okay, how do we find that? We can, one way to find it is think about what elements of the group share some factors with n. Okay, remember n is made of 2 prime numbers p and q. So the elements of the group that will share some factors with the n, let's think about only with p. Okay, so the elements of the group like 1 into p, which is nothing but p. 1 into p is part of the group, is not part of the group because it shares the factor p. Okay, 2 into p will also not be in the group. 3 into p, 4 into p, and so on. Q minus 1 into p. Okay, q times p will not be in the group because q times p is nothing but n. Remember, Z star n will not have n. So these are all the elements that share some factors with n, right? The factor that sharing is p. Okay, so these elements cannot be part of the group. Okay, And I'm also going to write a parallel line for this. What about numbers 1q? Yeah, it shares the factor q. 2q, it shares the factor q. And what about p minus 1q? Yeah, it also shares the factor q. All right. Again, p times q is n, so we will not have that written on this column. In both columns, p dot q is not present. Okay. Now the question we need to ask ourselves is that, is there any overlap, meaning an element present here is also present here? Okay. Just some little bit low-level details. P and Q are prime numbers. They are distinct prime numbers. Okay. All right. So let's think about now. Can there be any overlap between these two columns? Okay. Let's assume there's an overlap. So suppose there is some number I, such that I times P is same as J times Q. Okay. What can we say now? This means that Q divides I dot B, I times B. Okay, that's just the definition of divides, right? When a number divides another number, we can rewrite the denominator as a product of numerator. That's what basically divides means. Okay, so Q divides I dot P. But we do know P and Q are prime numbers. Okay, that means they don't have any common factors. That means Q must divide I. Okay, this comes from basic property of number theory, that if you have a number that divides a product and Q has no common factor with P, that means Q must divide I. Okay, what is that telling us? This is telling us that this is an interesting problem. Now, this is telling us that I is greater than Q. I cannot be equal to Q, because if I is equal to Q, then what happens is, let me finish this first. This tells us that I is greater than Q. Okay, but let me explain first here what are the properties of I and Q. Okay. In this column, what is the maximum value of I? I cannot be Q, because we are running from 1 through Q minus 1. So we do know that I is less than Q. I is strictly less than Q. Okay. So if you wanted to be more precise, when Q divides I, what can we say? We can say I is greater than or equal to Q. But you see, that's a contradiction. I is less than Q, but here we say I is greater than or equal to Q. That's not possible. Okay, that's contradiction because we assumed that there is an overlap between I dot P and J dot Q. That means there's an element here that is also present here. Well, if that is the case, we got a contradiction. Okay, the contradiction is that Q divides I, which means I is greater than or equal to Q. That's not possible because I is less than Q, because I has to be an element from 1 through Q minus 1. Okay, all right, so this is telling us that there's no overlap between these two columns. Okay, now we have to just count how many elements are in this column. This column starts from 1 through Q minus 1. That means there are Q minus 1 elements here on this column. And in this column, we have P minus 1 elements. Okay, so how many elements will not be in our group Z star N then? We can't have all these Q minus 1 elements. We can't have all these P minus 1 elements because they share factors with P or Q. That means we cannot have Q minus 1 plus P minus 1 elements in our group Z star N, because these elements share the factors P or Q. Okay, but how many elements are there in our original set? Original set is made of numbers from 1 through N minus 1. Okay, so there are N minus 1 numbers originally from 1 through N, excluding N, right? So we need to just subtract. We need to just subtract these two numbers to get the answer. Okay. And if you simplify this, remember N is PQ. If you simplify this and do some basic reorganization, you will get this is nothing but P minus 1 times Q minus 1. Okay, you have to substitute N by PQ. And I leave it to you as a homework to just check that this is equal to P minus 1, Q minus 1. Okay, so we have a nice formula now. The formula can be written as follows. If N is P times Q, P and Q are distinct primes, then pi of N the Euler's totient function, which is nothing but the number of elements in the group Z star n, is p minus 1 times q minus 1. If you know the prime factors, you can easily compute pi of n. Okay, let's just quickly run this thing through a Python program and check this is true. Okay, I'll get more confidence about this. Okay, let's do that. So let's define our p to be 5 and q to be 7. These are two distinct primes. And the n to be p times q. Count is equal to 0 for I in range 1 through n, which means n will not be part of the set. If GCD of I comma n is equal to 1, we count the value of we increase the counter, and then we return the count. Okay, let's see whether we can print now at least pi of n. Pi of n is 24. What was our n again? Let's print it. N was 35, p was 5, q is 7, and the assertion of the theorem that we proved was that pi of n was equal to p minus 1 times q minus 1, which is basically true, because p minus 1 is 4, q minus 1 is 6, 4 times 6 is 24. So we proved that pi of n is same as p minus 1, q minus 1. All right, that's basically it. We found a way to compute pi of n if we know the prime factors p and q. Otherwise, we don't know how to compute pi of n. And pi of n is actually very large number. It's pretty close to n, but it's not exactly n, of course. That makes it interesting because if you know n, if you know pi of n, you're breaking RSA, which we will talk later. Still, n is public. It's close to n. It's not so close that you can easily brute force the potential value of pi of n. That's amazing construction. All right, that's all. Thank you very much.